Hello everyone, welcome to the penultimate session of the Quantum Week of Fun. We now have Mekena Metcalf speaking about capturing dynamical correlation in variational quantum chemistry simulations using the double unitary couple cluster approach. Take it away.
Thank you, Nathan. It's great to virtually be with you guys. So today I kind of want to talk about extended basis sets. So when we're doing quantum chemistry calculations, in order to fully capture the electronic structure, we need to have virtual orbitals and be able to include effects from excited states. But most quantum chemistry simulations that you're going to see on quantum computers work in the minimal basis. And there's a reason for this. The reason is that including these virtual orbitals, which contain these dynamical correlations, can be a little bit problematic for near-term devices. So what are some of the consequences of having these larger basis sets, like a correlation consistent basis set? Well, the most obvious one is that you're going to have more qubits. And not that these virtual orbitals are super important, they need to be included, but you don't really want to waste qubits, which are a valuable resource, to be able to capture the energy. But another thing that's interesting is you also need more excitations when you're including these virtual orbitals in your active space. And more excitations mean bigger gate depth and also more optimization parameters that increases the dimensionality of your classical optimization routine for like a variational quantum algorithm. So our approach is to use concepts from coupled cluster embedding theory to downfold the virtual orbitals into an effective Hamiltonian operating in a reduced complete active space. This can be done by decoupling internal degrees of freedom containing the static correlation and external degrees of freedom containing the dynamical correlation. And this is achieved using the double unitary coupled cluster Ansatz. And which is exact in its general form for anti-Hermitian operators. So in this representation, the energy of the entire system is captured as an eigenvalue of the effective Hamiltonian, which we define here. And this is based on that ability to separate internal and external degrees of freedom. So we want to be able to approximate this external Hamiltonian using perturbative approaches or coupled cluster approaches. And we expand this in as a commutator to be able to do this cheaply. And then we're able to get this effective DUCC Hamiltonian that resembles our what we're familiar with these molecular Hamiltonians in the second quantized representation, where you have 1 electron terms and 2 electron terms, and the coefficients chi are obtained from DUCC. So though I say it is exact in its general form, we still have to make some approximations to be able to approximate this external Hamiltonian with this commutator expansion. You know, how do we include the many body effects in this DUCC Hamiltonian? And what is the approximate representation of the external coupled cluster amplitudes? And so I could also refer you to some previous publications by our collaborators outlining the theory behind DUCC. But where we're really interested in seeing how can we use DUCC with variational algorithms. So I won't go into too much detail about the variational algorithms since most people are likely familiar with this, but I want to point out a couple things. The first thing is that we are going to be generating a parameterized wave function for the effective Hamiltonian in the reduced active space. The other important thing is, what ansatz am I using? I'm going to be using the coupled cluster, unitary coupled cluster ansatz with single and double excitations. But also, I'm doing another little trick on these excitations to really get resource counts down, not just in the qubit space, but also in the gate space. And so what we do is we do an amplitude selection for the doubles based on Moeller-Plesset theory. And so we keep excitations that MP2 considers important, and we discard the rest below a certain threshold. And so I'll be able to show how the effects that this can have when you start to work in this reduced CAS space and also do amplitude selection using Moeller-Plesset theory. So to kind of give a broad overview of, all the different pieces behind this method that we're going to be implementing, we first start with the molecule that we're interested in, and we look in the correlation consistent basis, considering all occupied and unoccupied orbitals in that basis. We apply the double unitary coupled cluster Ansatz to downfold the virtual orbitals into an effective Hamiltonian in a reduced CAS space. Then we send that effective Hamiltonian to our VQE, and we have this UCCSD operator, this parameterized operator, acting on the wave function, which we feed to the classical optimizer until we eventually get the ground state energy of the effective Hamiltonian. So let's start with, the most obvious molecule to start with, which is H2. And so we have three different curves here. We have the orange curve, which is the full CI calculation of the H2 molecule with 4 spatial orbitals, no DUCC. The purple curve is the genuine full CI curve of H2 in the correlation consistent basis. And we can see the green dots are the VQE DUCC method in the 4 orbital active space. And as we can see, this VQE DUCC is able to capture the energy and the correlation energy that you're not able to do when you just straight up define the CAS's 4 orbitals. So the reason we can do this, and actually choosing the active space is a very important part of DUCC being effective. So if we look on the right side of the slide, you can see the orbital energies calculated using restricted Hartree-Fock theory for H2. And if we look 1, 2, 3, 4, you can see that those kind of are well-defined orbital energies. It kind of goes up again. And when the denominators of these orbital energies, if I was to look at like a perturbative expansion, if they are large, we can use like a couple cluster theory or something more simple. So that really tells us where we can define our active space to get our energy back. And then I want to draw your attention to the bottom of the screen, which is just kind of doing a little resource evaluation on H2. So we look at the 4 orbitals ones that we ran. This is spatial, so there's going to be 8 qubits for the spin orbitals. If we include all of the excitations, there's 15, and that's a depth of about 1,000. If we use MP2, and I will for all of these discard any amplitudes below a threshold of 10 to the -5, we see that it reduces the depth. But then if you kind of look farther, right, and you're like, okay, well now this is the DUCC Hamiltonian, what if I actually wanted to include these virtual orbitals directly onto my quantum computer? So if we go all the way down to 10 spatial orbitals on 20 qubits, there's 99 single and double excitations. It's a 16,000 depth circuit, and then that's actually where MP2 plays a really nice role. You can just discard a lot of those amplitudes and you can reduce it down significantly. So, okay, we did H2. Let's go on to something a little more complicated. So we're going to look at lithium-2. And so we evaluated lithium-2 for 7 orbitals and 10 orbitals using CCSDTQ to be able to get the energies. That's the dashed lines up top. The VQE DUCC are the ones below in purple and orange as well to compare to. And we can see that the energy gets better. But you might be wondering, what is this bump for the 7 orbital one? And that actually is from not having a very well-defined active space. So if you look again to the right, you'll see these Hartree-Fock orbital energies, and it's very difficult to distinguish where one should put their CAS space. So we can kind of see that 10 orbitals is really optimum, maybe even a little bit bigger. So we actually are able to get rid of that unphysical bump as we add in more determinants needed for the static correlation. And it's this competition between the static and dynamical correlation. So this is like, okay, so you have this challenge, like, how do we choose this active space? Well, there is a natural way to do so. So we can look at natural orbitals, and natural orbitals can be obtained by diagonalizing the density matrix of the atomic species to determine which orbitals are most probable. And we can get this wave function easily using Moeller-Plesset theory. And this is the green curve. But as you can see, like I said, we use Moeller-Plesset theory. So we didn't go out to long bond lengths where Moeller-Plesset theory fails. And so we really need to have a good way to describe in an approximate way this wave function. So that's something we'll look into further, are using different types of methods to be able to get this, these natural orbitals. So with these natural orbitals, this is the green curve. This is in the 7 orbital, which, as we showed before, was not a very good representation. All of a sudden, the bump is gone. We've captured more correlation energy. And more exciting than that, we actually captured the dissociation energy of Li2 compared to the full CCSDTQ, which was about 60, like a 60 spin orbital calculation, or no, 60 spatial orbitals. So it'd be like 120 qubits to get that energy, and we can do it with 14. And you can also see that you're able to capture the dissociation energy better, even without using the natural orbital representation and using the VQE DUCC. So to do a little bit of a resource count and kind of to tell you the story of the difficulty of VQE, this was actually a very challenging VQE problem to solve. Using our simulators that we have, I used QCxQC. These are older versions of QCxQC. They've updated it. I think that solves some of these problems, but I'll tell the story anyways. So we're kind of working in this 20 qubit space, 14 to 20 qubits. We have a ton of excitations. We have a really deep circuit. So this is like actually a pretty hard thing to do. And furthermore, it took around 10,000 steps to be able to converge to the ground state energy. And so with the previous software, it was compiling that circuit for every single step, executing it. And this took to generate a curve took about a week to be able to do, classically on my classical computer, which was kind of frustrating. But as you can see, like thinking about the dimensionality of the optimization problem, compiling these deeper circuits, especially if we want to look at molecules in the supremacy regime and we want to compile these circuits, we see how software starts to play a big role. And our evaluations of molecules like Li2 can be really demonstrative of where improvements in the software can be made. So drawing our attention to the resource count, we can see, so I did the 7 orbitals, I left 10 off, but if we go up to like 13, right, 26 qubits, that's not really big. We're looking at over 1,000 excitations. That's a very high dimensional optimization problem. It'll take forever to converge. We have depths in the hundreds of thousands. Then we use MP2 and we actually can reduce it to like a more manageable problem. So that's good. And we definitely needed to be able to do this to even get our programs to run. It seemed like amplitude selection, when you start to go up to bigger molecules, was just absolutely necessary. And what was fascinating is if I just included the singles and these perturbative doubles, I was able to capture the energy, not an MP2 energy, but the actual energy of the Hamiltonian using the UCCSD. So even though one might think, oh, I'm only going to get MP2 energies, when you feed this to the optimizer, you actually start to get better energies and can get well below chemical accuracy. So the last one, Nick kind of showed this reaction pathway. So we're going to look at beryllium dihydride and the reaction pathway, where we have on the left, that is the A, that is the chain. So that represents the symmetry group 1A1, 2A1, 3A1. And on I, there is the, when they're separated by a longer bond distance, which is 1A1, 2A1, 1B2, where you have this p orbital in the beryllium. And as they start to come closer together, these two determinants, these two symmetry configurations become degenerate. And so we want to test, how does DUCC work with these degeneracies? And furthermore, how does natural orbitals work when you have these degeneracies? So the top one, the RHF in orange, is the CCSDTQ in the 6 spatial orbital space with these restricted Hartree-Fock orbitals. And we see below the purple curve is the VQE DUCC in that same space. So yes, it captured more energy. It looks, the shape looks very similar, but then we can see with the natural orbitals, we can even get a better energy. So, you know, just to tell the story of doing some of these calculations, this was actually a challenging problem also to be able to do this with VQE. And the choice of Ansatz when you have degeneracies was super important. And this is because as you go through these reaction pathways, you start to see level crossings between the singlet ground state and the triplet ground states, even some doublet ground states. And so this starts resulting in local minimum and your optimization space as you start to get closer to these degeneracies. And so you really have to carefully consider how you construct your Ansatz and your initial point so that you don't find yourself stuck in these local minimum. And this was specifically challenging around the geometries in the degeneracy area. So, you know, there's lots of little things to think about as we start constructing these and applying all of our methods to real problems. There's the software side and making these things more efficient, so we're not taking a month to run some problems. There's also, you know, how do we construct Ansatzes by being cognizant of the structure and the energy diagrams of the Hamiltonians, as well as how do we deal with degeneracies when we are using something like VQE. So I will conclude after this. So we talked about how having more virtual orbitals from larger basis sets to capture dynamical correlation in the active space has a big resource overhead. But downfolding virtual orbitals into an effective Hamiltonian using the double unitary couple cluster Ansatz in a reduced complete active space captures this dynamical correlation. Third, amplitude selection resulting from perturbative techniques combined with an effective DUCC Hamiltonian significantly reduces gate depth of working with these larger basis sets. And lastly, natural orbitals obtained from less expensive methods provide a more natural active space and result in more accurate energies. With that, I'd like to thank my collaborators, my supervisor, Bert, and our collaborators at Pacific Northwest National Lab, Karol and Nick, and also our funding agency through the Department of Energy, Basic Energy Sciences, for the team embedding quantum computing into many body frameworks for strongly correlated molecular and material systems. Thank you.
Thank you for the nice talk, Mekena. There was some very large calculations. I can see why that took so long.
Yeah, it was like really getting your hands dirty doing VQE, which was nice. And I feel that people have avoided that. We want to work 2-qubit, 4-qubit kind of experiments. And we're planning on running something on a quantum computer. But I think it's nice to say, how are these variational algorithms going to work when you start moving into the supremacy regime, right? You know, 50 qubits, that's a big optimization problem. And counting these configurations and all of these excitations. So, yeah.
Out of interest, what optimizers were you using for these large parameter optimizations?
What? Sorry.
Out of interest, what optimizers were you using for these?
I tried different ones. I liked the Kowalski optimizer, the non-gradient based. This was because when I was running some other molecules that I didn't present, I was finding crazy things happening. We heard about barren plateaus, but there's also these things called ridges. And as I was using the gradient descent, it was just going all over the place. And Kowalski, which was a non-gradient base, kind of seemed to circumvent these problems. Yeah. Though it might not be the fastest, it might not converge the fastest, I found it was accurate all the time.
That's interesting. I think, like from some of our experience, when you get to the really big parameter things, some of the neural network based methods can be a bit more quick, like TensorFlow, for example. Yeah. And I think that's what I was kind of saying. When you go to 1,000, you know, your little SciPy optimizers might start having a hard time. Okay, so there's a few questions Slack. So we have one from David Munoz-Ramo. I guess this method requires a physical ansatz in order to define the excitations and perform the downfolding process. So it's not applicable to the hardware efficient ansatz.
No.
Yeah.
No.
Makes sense.
Yeah, the downfolding is based on couple clusters theory explicitly. And then the ansatz, you could use the hardware ansatz with the DUCC Hamiltonian. Those are independent. I chose the UCCSD because it really just makes a lot of sense to me, and I'm able to think about the molecule and how I'm setting it up. And I can apply this MP2 method.
Yeah. So with the natural orbitals, obviously you're cramming as much of the electron density into the the smallest amount of the excitations example. For example, so have you tried truncating it and seeing how the energy changes when you're in the natural orbital basis?
Truncating
the excitation space.
The excitation space?
Yeah.
Yes. Yes. And it works. It works.
Yeah. Nice.
Sorry.
Was that better than using the standard SCF MOs?
Yes. Yeah, okay. It was a better way to define the active space. And like when you saw with the lithium, they were all like really, really close together. So it's like, where do I actually like define my active space? So when you look at the probability weights, it's like, okay, this is where we want to.
Yeah. There's a second question from David Munoz Ramo. It says, is there any situation in which the MP2 pre-screening amplitudes may struggle to find the negligible excitations?
So if the pre-screening amplitude, so when I do the amplitude selection for the MP2, if that will struggle to find what?
So it will be bad at screening, essentially.
I don't know. I haven't tested that.
Yeah. I mean, it seems to be quite
like electron screening from core.
Yeah, I think so.
Yeah, we included all electrons, so we didn't look at like considering just the core and the valence. But I think that would be a really fascinating thing to look at, you know, and testing the validity on different types of molecules of this amplitude selection. It was kind of just a trick, but I haven't wrote a formal paper about it yet.
Yeah. I mean, it's very powerful that you can get such good results from doing MP2 pre-screening.
Yeah.
Yeah.
Yeah, it was a surprise. I had to really convince my collaborators. And then I kept it dynamical, right? So like, I didn't just fix the MP2 amplitudes for all distances. I recomputed it for every distance. So like, I might have more amplitudes at shorter distances than at longer distances. I found at longer distances, that's where you started to see some problems with the MP2. But if I included the singles, that went away. Because at first I was just doing it with the perturbative doubles and it worked. But then at longer distances, it didn't work. So that's when I added the singles back in and I was able to recover the energy.
So the singles bring back the correlation that the MP2 is.
Yeah, that static correlation that's necessary to parameterize the ansatz.
Very interesting.
Mm-hmm.
Okay. We had another question on the Slack from Gabriel Green Diniz. Is it possible to get an effective Hamiltonian by downfolding the orbitals in a spatial basis in order to embed a molecule in a larger environment at a lower level of accuracy? So kind of like a multi-layer sort of levels of theory. Would the downfolding work in that respect?
I think I'm still a little confused by the question.
So do you think you could use the downfolding method to embed into like a DFT?
Yeah, probably. Yeah. I could see it. It is not necessarily needed for a quantum computer. It can be used for different methods as well. Yeah, as defining nice active spaces for ED or DMRG, things like that. Definitely.
Yeah, that's very cool that it could be used in classical method. So from Hans Chan, he says, great talk. And is there an archive paper?
Yes, and there's going to be a JCTC out probably next week. I'm just finishing the final proof and that will be out, but there is a paper on archive and I don't know why I didn't put it on my slides.
Okay. And then I guess with this natural orbital basis, have you tried using these adaptive methods that you've seen? Because I think that would be a really nice way to exploit.
Yes, like the adaptive VQE.
Yeah.
I had huge problems with it. Yes, I used it for the BEH2 because we were really struggling to get that to converge. So we tried different ways to get the Ansatz, and it actually didn't converge, is what happened. So you can kind of like, it's like stuck in this loop as it's trying to add more things in, and that just kept happening. And so I got really frustrated and went back. And so what I actually did to figure it out is I created my Ansatz as a triplet Ansatz and included triplet excitations. And that's where I was like, okay, this is what's going on. So we really need to make sure we're looking in the singlet domain and not including excitations that might lead us into a triplet type domain.
Yeah.
Or doublet.
I feel like the natural orbital basis and adapt are like the perfect match. If
yeah.
That would be really good.
I would be interested in trying it on different molecules. I only tried it on that beryllium dihydride. And I did have problems, but it wasn't, I don't think it was the fault of the natural orbitals. It was a very hard problem to test it on.
Yeah, cool. Okay, well, thank you very much for your talk. It was very nice. I hope you have a nice rest of your day in California.
I will. It's sunny and not smoky, finally.
It's raining in Cambridge. But it's actually not, I'm lying, but most of the time it is. Okay. Thanks a lot.
Absolutely. Talk to you guys later.
Bye.